In continuation to the previous lecture, today we will start enzyme immobilization. During the production of commercially important products via enzymatic catalysis, soluble enzymes have traditionally been used in batch process that employ some form of stirred tank reactor (STR). In these processes, at the end of the batch run, the product must be separated from any unused substrate and also from the enzyme catalyst. Removal of the enzyme at this stage can be achieved by thermal denaturation only if the product is thermostable or by ammonium sulfate precipitation or ultrafiltration. These processes represent a costly downstream processing stage and generally render the enzyme inactive. So when a new batch run is to be started, a fresh batch of the enzyme is required. Immobilized enzyme system, in contrast, fix the enzyme so that it can be reused many times, which has a significant impact on production costs. As a very simple example, if an enzyme is mixed with a solution of warm but not too hot, solution of warm agar, and this is allowed to set, the enzyme will be entrapped. For the purpose of this example, let us ignore the fact that the enzyme will gradually leak out of this gel. The agar can then be cut up into cubes and then can be replaced in a STR together with the substrate as shown in the figure. This is immobilized enzyme. Again, the reaction would be allowed to proceed and it might actually be slower due to diffusional constraints. At the end of the batch run, the catalyst can now be easily separated from the product by passing the reactor contents through a coarse mesh. Immediately, an important downstream processing step has been carried out, and just as importantly, the active enzyme has been recovered so that it can be reused for the next batch run. This ease of separation of enzyme from product is a major advantage of all immobilized systems over their counterparts that used free, that is soluble enzyme. This figure shows the stirred tank reactor containing immobilized enzyme. This physical advantage of ease of reuse of immobilized biocatalyst is one of the main reasons why such systems are favored commercially. However, immobilization may also produce biochemical changes that lead to enhanced biocatalyst stability, which may be manifested as an increased rate of catalysis, prolonged duration of catalysis, and third is greater operational stability of extremes of pH temperature. The particular advantages conferred by immobilization will therefore differ from one system to another. It should be noted that often there may be no biochemical advantages at all, and the simple physical advantages of ease of separation of biocatalyst from the product may be sufficient to favor the commercial development of an immobilized process. This figure shows continuous flow reactors. A indicate continuation flow stirred tank reactor CSTR and B is packed bed reactor PBR. Once a biocatalyst has been immobilized, it can also be put in a range of continuous flow reactor. Enable a continuous supply of substrate to be turned into products as it passes through the reactor. The control of such continuous flow reactors can be highly automated, leading to considerable saving in the production costs. For example, a STR can be easily modified to produce a continuous flow stirred tank reactor as shown in figure A, in which the enzyme is held within the reactor by a coarse mesh and the product continuously flows out of the reactor as substrate is pumped in. It is also possible to produce a packed bed reactor PBR figure B, shows in figure B, in which the agar cubes are packed into a column and the substrate is pumped through a bed without any need for stirring. CSTRs and PBRs enable the enzymes to be reused many times before it needs to be replaced. For example, in the production of the high fructose syrups, the immobilized glucose isomerase enzyme would typically be used continuously for between 2 to 4 months, and only after this time, when its activity would have dropped to 25% of the original level, would it needs to be replaced. The overall operating cost of continuous flow reactors are often significantly lower than those of equivalent batch processes. Batch reactors need to be emptied and refilled frequently at regular intervals. Not only in the procedure expensive, but it also means that there are considerable periods of time when such reactors are not productive, so-called downtime. In addition, batch processes make uneven demands on both labor and services. They may also result in pronounced batch-to-batch variations as the reaction conditions change with time, and they may be difficult to scale up due to the changing power requirements for efficient mixing. Due to their higher overall process efficiency, continuous process using immobilized enzymes may be undertaken in production facilities that are around 10 to 100 times smaller than those required for equivalent batch processes using soluble enzymes. Therefore, the capital cost involved in setting up the facility are also considerably lower. This figure shows the immobilized techniques.